Okay, what this lecture is about, what it says on the slide, structure of materials. All materials have structure. This is the heart of what material scientists live for, is really understanding that structure and correlating that structure to the properties of the material that we end up getting. So let's begin. Here we go. So here's a big idea. And nothing in science is really simple if you look at it close enough. If you closer and closer you get, the more interesting things often become. Think about anything you know about, a piece of chalk. If you really delve down, it's a whole bunch of particles that are stuck together. Some of them might be little fossils in themselves. They all have a story. They were compacted together to make that and slough off in such a way that it leaves the white trail behind it. Just look at your fingernail. There's actually a whole lot of structure that's sitting back there in your nail, beneath your nail. What holds it together? What makes it hard? What makes it pliable? A car tire is really interesting. This composite on many length scales. It's mostly rubber, but there's steel belts in there. There's other bits of Kevlar. There's carbon black to give it optical properties and to help it weather UV. Even if you look at a steel nail, what could it be simpler than that? There's all kinds of phases. There's crystals. There's little bits of carbide in there. There's a grain size that's being stabilized by those carbides. It has a certain hardness, a certain ductility. All of these things, all of these very simple things, and anything indeed that you look at, has really all kinds of features at all kinds of length scales, and those features are what lead to properties. That really is the heart of what material science really is all about. So the learning objectives for this, we want to describe what we mean by the word microstructure. Microstructure is really a series of features. We examine those in a certain way and show you what they look like. In the mode of this class, we're going to talk a lot about size scales and use that as a way of bringing math in and understanding the world quantitatively. We'll introduce a little bit of vocabulary, for example, the word phase, which is a very important word for material scientists. And we'll talk about how we interrogate that structure, how it comes about, and what we end up doing with it. So let's start with something big, something you might be familiar with. If you've got a nice kitchen, you might have these kind of granite countertops sitting in there. These things are usually something on the order of about 8 feet and change by about 5 feet. They actually come from big quarries all over the world where they're taken out in big chunks. Those chunks are sliced up. They're polished, something like this. Your countertop might come out of that, be polished. There it is. It ends up in your kitchen. Some great YouTube videos on how this all works. It's an amazing thing. It's amazing that it's become so affordable in the past several years. Here's one example, YouTube. There's many of them out there. If you just put in mining or preparation of granite countertops, it's a marvelous story. The reason I like countertops is it shows you exactly this kind of structure that we're talking about in material science, but it's at a much larger length scale, one that's easily accessible. And then we're going to talk about the countertop first, then scale down to really small stuff. So here's granite. We'll call this one Granite 1. We had our kitchen redone over the summer, and so I got into one of these places. They've got all these bits of granite. It was remarkable. As a material scientist, I was just incredibly geeked out. Again, these things sit about 8 feet the long way, something like 5 feet the short way, and every one of these tells a story. It's a story about how the Earth was made. Somehow some rocks came together. They were under heat. They were under pressure. The chemistry came together and formed some kind of a pattern. You can look at that pattern. That pattern tells a story. Usually what we do as materials people, we try to work the other way, where we try to design a structure, design something that has a structure we like, that gives it properties, but this is just what nature gives us, and the property we're looking for is something that's beautiful we can make our countertop with. I don't know how this thing was made. This is probably layers of sediment that look like this. You can see this layer is different than the others. You can see some waviness. Maybe it was a stream bed. I don't know how it was made, quite honestly, but it is beautiful, and it does illustrate a lot of the things we're interested in. First of all, material scientists almost always put scale markers on their micrographs. This one's about 8 feet long. This whole thing is about a little over 8 feet side to side, closer to 9 feet. You can see different colors. The different colors usually end up being due to different chemistry or different phases. You can see these areas here look similar to one another. They might look way more crystalline. That's probably where there is some completely different material. It might have a different crystal structure, different chemistry associated with it. These we will define as different phases in a little bit. That's one example. Here's another one. Again, granite and any piece of material can tell a story. This is kind of an inset box over here, and this one has all kinds of little fossils and shells in it. This is just a blow-up of this area. So this one here, this might be something like 10 inches. This is about 4 feet across here. And again, it tells a story, and this formally is a composite. It's basically a rock that might be made by sand that came down, ended up being pushed under pressure and temperature, and then you have these what were organic materials, which were shells that were also pressed into it, and the whole thing ends up sitting together. And again, the important part of this for your kitchen counter is it's a real thing of beauty. This one, I have no idea how it is made. It was really beautiful, but you can see in materials we often see something like this, where we've got sort of the centers of some sort of grains, then often things grow out and they meet at boundaries, and you can see these are boundaries between these these regions that are somehow similar. These boundaries and crystals or some kind of feature that sits between boundaries is a common feature in material science. One will come up with a lot. Just thought this was pretty. Again, I don't know how it's made, but again, you can see discrete areas. This is similar to this. You know, these areas here are similar, and there's properties. If you're going to break this thing, I might guess that it might end up breaking along a certain type of feature. Maybe this really light feature, maybe this. They usually have different mechanical properties, different electrical properties, depending on what the structure looks like. And that's part of what makes material science fun. Another kind of interesting example, this one looks much like a regular material. This looks almost like a steel microstructure, is why I took the picture. You can see something going on here, and then something going on in these other darker areas. If I zoom in on an area like this, you see there's indeed other structure here, and I would hazard to guess, and you can see there's some predominant alignment along these. I would hazard to guess that these are crystal of one chemistry, this is crystal in an area of another chemistry, and these all fit together to form some kind of a microstructure. Again, in one lecture we can't get too deep into this, but it does show more or less how this comes from and how this stuff is pervasive. Once you start looking at the world this way, you see these microstructures and these kind of features everywhere, and if you can reverse engineer them, you can do some pretty neat things. So anyway, this is what we material scientists call microstructure. I'm going to show you a few examples. Again, not going to make you an expert by any stretch, but give you the key ideas. So first of all, we know materials are made up of atoms. This is a picture down here that shows maybe a schematic of atomic stacking. The distance between these things are usually on the order of 2.5 angstroms, which is 2.5 times 10 to the minus 10 meters, which is by unit conversion the same as 0.25 nanometers. That's what we're talking about. And you can see what this shows is there's regions here that look relatively ordered, and then there's boundaries between these ordered regions that look somewhat disordered. These ordered regions we call crystals. The areas between them we call boundaries. We go up in size scale many orders of magnitude. You get what's up here at the top. This is an image that was developed by some kind of complicated techniques to show off every color is a different crystal, and between these crystals there's intercrystalline boundaries. These intercrystalline boundaries we call grain boundaries. Pretend that says grain boundaries. And these other regions here are what we call grains, and they're crystals, grains and boundaries between the grains. That's a fairly simple example. And this is a as-cast wrought aluminum alloy. Another vocabulary word in here is wrought. Means actually not sure what this. Wrought means worked, which is different than as-cast. So it says as-cast wrought wrought grade aluminum alloy. I think this is a working grade, but it's cast. But be that as it may, this is what's important: is you've got these crystals and boundaries between them. And there's a number of techniques by which we can take these crystals and color them based on their orientations and make these beautiful and technically informative figures out of them that really convey a lot of information. Hopefully by the end of this lecture you understand how these things fit together. Another example we're going to use a little bit here is shown on the right side here. This is an example from a superalloy. And the way we make superalloys is they're based on nickel, and there's a nickel-based material here, and then there's another phase inside of here, phase meaning that it's chemically distinct in the middle, which has a chemistry Ni3Al. 3 nickels and an aluminum come together like that, and they form these little things we call precipitates in there, precipitates, depending on who you talk to. Those are seen there. And those two structures put together, if they're fine enough, make something that's really, really strong, because there's defects that have to pass through this, and these defects here, these are something called dislocations. And they have to pass around, those defects. It makes the material very, very strong. And again, you get these beautiful images that are also technically very deep, and this is what keeps we scientists really, really entertained. And this is what keeps the scientists entertained, and what keeps the practitioners really employed, is that we know how to make these kinds of structures that have these remarkable properties associated with it. These are the materials, showing a little bit, that operate at about 90% of their melting temperature in the back of aircraft engines with remarkable reliability. And it's this structure, this microstructure, that's really at the heart of it all. So again, we're going to talk about scale, and we're going to talk about it over many orders of magnitude. So scale and powers of 10. This is a topic that came up in a past lecture of mine. I mentioned one of my favorite little YouTube movies, IBM's Powers of 10. There's a Simpson version of this. Down at the bottom, Cosmic Voyage with Morgan Freeman did more interesting versions maybe than the IBM classic, but they're all really good. Pick one you like, show it to your students. It is mind-boggling. If you get into the right mindset, it's something. So again, if you think about length scales, remember in the metric system we usually do things in factors of 1,000. If we start with our base unit as a meter, 1,000 meters is a kilometer, 1,000th of a meter is a millimeter, 1,000th of a millimeter is a micron, 1,000th of a micron is a nanometer, 1,000th of that is a picometer, and then you get down to femtometers, and not much happens down here. This is proton diameters. Atomic repeat distances sit here, mentioned before, about 2.5 angstroms, and it's kind of from here to about here. This is really the range of length scales that we really consider material science. It's going from these atoms to how they fit together, and you can see this is a factor of about 10, 20, 10, 100, 1,000, 10,000, 100,000, a million, 10 million, or 100 million orders of magnitude or factor of that is what we're looking over. So it's a big deal. Big differences. So again, atoms sit here. These strengthening clusters sit about here at a range of about 10 to 100 nanometers. Bacteria sit here about a micron. Most of these crystals that we're talking about in materials sit here. So you can see, counting down, there's usually several thousand grains across fit into a crystal, and then several hundred crystals might make up the width of a fingernail. It's about this kind of scales we're talking about. So what's really interesting, really difficult in material science is trying to understand things at these really short these short lengths, and then connect them to phenomenon that are happening up at much larger lengths, and that's really a key challenge. Again, one that is, for most of us scientists, called job security. So again, key length scales we're going to be dealing with. An atom sits here at about 2.5 angstroms. A nanometer is a very small length. Most grains sit here in the micron range, and most things we deal with are out here in the millimeter range, and that's, again, sort of the key length scales in material science. We'll keep coming back to this. So most real materials are really engineered microstructures. This is a superalloy problem I told you about before. Any airplane that runs with a jet, most of the advanced ones back here, have engines. In the hot section of these engines, the efficiency of the engine is all dictated by how hot we can run everything. So we want to take nickel-based materials and run them at something like 90% of their melting temperature. The way we do that is by making these structures, which we call gamma prime structures, where, for example, the gamma is nickel, and then the gamma prime is Ni3Al, and the gamma prime are these little guys here. And by heating the material to high temperature, quenching it down, aging it just right, we can make these remarkable structures that have remarkable high temperature strength. So again, I've kind of gone through a bit of vocabulary. So a grain and a grain boundary is a crystal, and basically the boundary between the crystal. A phase is a region that's basically identifiable, both in its chemically homogeneous and has a distinct structure that is identifiable across that region. A solute is an atom that sits within the crystal, and I'll show you an example of that in a little bit. And then within this, we have all kinds of defects. We have point defects, which are basically missing atoms or extra atoms or solutes. We can have line defects, which are called dislocations. We have planar defects, which are like grain boundaries, and then we can have volume defects, which might be like holes. And again, these happen over many orders of magnitude. Atoms sit down here. Grains usually sit, sort of in this region. And then defects usually are back down here and are quite small, and typical sizes in the nanometer sorts of regions. That's where your defects typically are. Putting all that together does make the head spin sometimes. So again, going back to the nickel-based superalloys, this is again what kind of puts all these things together. You've got the gamma matrix here, which sits here, and this has a size scale. Bringing back to my size scale, you can see this is 300 nanometers. Going back here, 300 nanometers sits in about that range, right about there, less than a micron, but many atoms thick. And my gamma prime particles sit here like that. My gamma prime particles, in turn, look like this, where my features sit about 2.5 angstroms this way. And it's like a brick and mortar structure, and that all is how that fits together. And this all together is what we call microstructure, all the way this stuff fits together. So again, definition of the phase, I've mentioned it quickly before. It's a region where all physical properties are essentially uniform, and that means they're chemically distinct from what's somewhere around it. So as an example of this, you might have a jar that might contain water in the solid state and in the liquid state. So ice would be a phase, liquid water would be another, and if there's water gas above it, that would be another phase. Oil and water, if you heat them up, might be all together in chicken soup, or as you cool it down, they phase separate. In one case, that's one phase. If you cool it down, they phase separate into two phases, an oil-rich phase and a water-rich phase. Recognize even if the thing that you think is water, there might be some oil dissolved in it. All of these topics persist in the solid state as well, what's soluble and what we define as solubility. All that stuff moves into the solid state as well. So again, I mentioned before, most materials are made up of a bunch of grains fitting together. Grains are the same as crystals. And crystals are atoms lined up very orderly in rows like this. So each of these crystals in this region is like that, and each one might have a different orientation, where the crystals are lined up one way in one grain, a little bit differently in the next one, lined up a little differently in the one after that, and then lined up differently in the one after that. That's how These things all fit together, and these areas where they come together we call the grain boundaries. These crystals are important because if I take this thing and pull it this way, I see a different stiffness than if I might pull it along a cube diagonal. It's a little bit easier to see here. In this case, this is what we call a body-centered cubic crystal. Body-centered cubic, as we see in iron. If I pull it along this direction, this cube diagonal, this is the close packed direction. These guys end up touching each other, basically. That gives us a very high stiffness. If I pull it along this direction that isn't so close packed, I get a stiffness that's about half that. So these grain directions actually do matter, and they are distinct, and where they come up to boundaries, some very interesting things can happen. And you can see as from the pictures before, things are somewhat disordered as well. So these are single crystals. This is a polycrystal. We see this in real life as well. This is a polycrystal that might be rolled out like this, and in manufacturing we do all kinds of rolling. That can change the average orientation. It can also make the grains longer in this direction and shorter in the other direction, as you see. You see that average pancaking of the grains. Most cases, things are relatively random. You see here relatively equiaxed grains, and equiaxed and random aren't necessarily the same, but there are ways, multiple ways we can figure out if things are really randomly oriented, and we can look at the microstructure this way. So how do we interrogate materials? The simplest approach, so we call optical microscopy. It's much the same as what you have if you have like a granite countertop. What we do is take the material, slice through it, polish it, and then we often put a little acid on. That acid will attack the crystals differently depending on on their orientations, their crystalline orientations. And then you get patterns out that look like this. You get contrast between them, and then typically that might be something like 20 microns. Scale marker might look about like that. And each of these is basically a crystal, and these lines between them are where there are different orientations within that crystal. That's called a twinned crystal. Understanding those structures, again, really is the key to material science. Making good ones is what we really want to do. The other thing that's very compelling about this field, these microstructures can be beautiful. This is just an example of one that's a cast microstructure. These things are dendrites, where the crystals end up growing like trees, where you've got branches and littler branches off of those. And these things look very often just like pine trees. You can see these suggested like that. And this is, again, a planar cross-section that's taken through that. And you can see these are big crystals, and then there's some action with smaller crystals happening in there. And lots of things going on, and understanding that is really important. And again, there's some great websites. This website out of Cambridge, England, something like dissemination of material science through IT or something like that is what that acronym means. It's a very good site with lots of micrographs on it. So that's optical microscopy, is that technique. That's what's used for. You can also use electrons to do this. We have some very expensive equipment here at Ohio State to do this. You can do a lot of things with this. You can do imaging. I'll talk about diffraction. You can determine chemistries. And all of this can be done almost at the atomic length scale. And I can't even begin to do justice to this in this course, but it's a powerful thing. But I did mention in here, imaging is what we did with the optical microscopy. This is an image. Anything you do with a camera is an image. The other thing that's important is diffraction. And diffraction is really a different way of looking at things. And that's an interaction between a wave and a crystal, and it gives you patterns that come out of this. And it's just to say, a different way of doing things, and you can get different kinds of information. So this is a nice example. This is an X-ray tube. You get these waves that come out of this. These waves are a characteristic wavelength. Those reflect off of the atoms themselves. They might interfere. They do interfere with each other constructively or destructively. And you get these diffraction images that come out, diffraction patterns that come out, where you see certain angles have very high intensities associated with them. And those areas, these are areas where you get constructive interference, and you can solve for the crystal spacing and orientation by running experiments like this. You can do this with X-rays of a certain wavelength. You can use white X-rays also and determine crystal symmetry. You can see there's specific directions in that. With that, you can solve everything there is to do with the crystal, and this goes back to Bragg, and I think this was about 1900 that all of this was done for the first time. X-rays do this because X-rays have wave qualities. Electrons can also have wave qualities and do all of this also. Very neat stuff. But anyway, after we've done all that, and all of this has been solved a long, long time ago, and I'm not going to go through that now, but you find that there's some, that these crystals have structures. There's orientation, there's symmetry associated with it. You can see that that these directions, A, B, and C, are basically equivalent. These diagonals are different, and there's symmetry operators associated with that. That comes out of this. The other thing you can see is that there's regular patterns associated with the packing. This is the sodium chloride table salt structure, where these are the larger chloride anions. These are the smaller sodium cations that sit in there. They form this structure. This is another structure, the zinc blende structure. This is the structure here of graphite, which basically has covalently bonded carbon sitting in layers, and these are held together with secondary bonds. Remember, we talked about secondary bonds last lecture, and one of the things that's cool about graphite is these are really, really strong bonds. You can make really high property thing with graphite, but then you can also use it as pencil lead, and when you do pencil lead, these layers basically slough off of the bottom layers because they're hardly held together, just held together with secondary bonds. So again, in this scale, everything I'm showing you is down here at the atomic scale. These interatomic spacings are on the order of about 0.25 nanometers or so. I go up many orders of magnitude in length scale, and this is in the several micron to millimeter sort of length scale. We can look at structures at higher length scales. This is another example of dendritic solidification. These things look a little like pine trees, and I can tell you it's a cast structure just by looking at it. You get very similar structures on your windshield in the winter. That's cast. The other thing that we do with materials often is we work them. The past tense of work is wrought. That gives us a wrought structure. And then usually things are equiaxed. You see these grains have about the same dimensions in both directions. And this is a cast structure, this is a wrought structure, and you can determine that very quickly. If we do something like a weld, what we end up doing is melting the material and letting it solidify. This weld structure, this is something that's much like a cast structure. It really is cast structure. Then this area over here has not been melted. That's wrought. And then there's this other area in here. This is called the heat affected zone, HAZ. And you can see the heat of this casting affected the material in this region. And again, if you're making cars, knowing all this stuff is really important. And there are more than a few engineers that obsess on exactly these structures, what the hardnesses are, the properties, how you control that, all that stuff. Good careers. Good careers. Again, back to all this, these are still can be described as crystals with boundaries between them. So again, these are the crystals, these are the intercrystalline boundaries. Kind of covered that. If I zoom way in on that, go from, again, go from the length scale that's out here, or more like here, out in the several tens of micron length scale, looking at length scales in this kind of region. I can go down, look at length scales of this kind of region. These are basically atoms sitting here. This is 2 nanometers. That's what that length scale is at. You can see the atoms fitting together and forming these fairly neat boundaries in that case. Sometimes the boundaries are messier than that, but you're basically seeing the atomic contrast between atomic planes there, which is pretty neat. So we can study things at multiple length scales. The other thing we're really interested in is looking at very small particles. Early stages of forming these precipitates is really important. Again, length scale here would be about 100 nanometers, sitting about here. And these are small crystals, very small crystals. There are still hundreds of atoms across that are forming in aluminum. We have great examples of how we use this. At Ohio State, we've got great facilities for doing electron microscopy. We use this for all kinds of problems. One of the problems I was working with a team that we worked on is looking at cracking in materials that are used in high temperature componentry, and we can understand the crystal orientations with the tools we have. We can see how the cracks form, and then we can also look at how variations in the structure affect that process. This is how we make materials better, by going through and understanding it, understanding how to modify the structure, and make them better. And again, in this, you can see the length scales we're at. We're usually up here in 50 or 100 micron kind of level, so up here, approaching millimeters. So again, key vocabulary that comes from this is the idea of a grain is a crystal, a phase is a physically distinct area, solutes can sit within the grains, and we have all these defects that sit within this, and over this whole thing we can span many orders of magnitude in length scales. The big conclusion here is microstructure is really at the heart of material science for all classes of materials. Most of my examples here were metallurgical, and by changing microstructure we can change all kinds of properties, and this is what metallurgists do, and this is what nature has done for a long time. Whenever we look at biological structures, there's also a structure there, and that structure leads to the properties that we end up getting. I think that's it, and look forward to seeing you next time.